thinking polar coordinates and whether we can use the imaginary numbers.
I was just thinking about the signal feed-outs of...
Some of the students around here are figuring out how to use artificial intelligence to solve problems related to space weather.
So we can use Bayesian statistics to determine the error bars for our estimate.
The integration problem is going to be really hard for that. We're going to need to introduce some complex variables into the problem.
But the stochastic properties of this measure does not allow us to do that.
Now, someone eavesdropping on this conversation might not really understand these mysterious mathematical mutterings. They're puzzling, perplexing, and indistinguishable from nonsense.
Sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side.
For some, mathematics might feel like an exotic language that's only useful if you're a scientist or engineer. But the appeal of mathematics is actually far broader. It makes nature comprehensible and predictable. I'm Seth Shostak.
I'm Molly Bentley. This is Big Picture Science, produced at the SETI Institute, and in this episode, clever ways to open your mind to the beauty and usefulness of mathematics, including a proposal for rethinking how we teach it in the first place. It's Math's Paths.
Sharpen your wits and your number 2 pencils, because this episode contains a series of mathematicians.
I'm Steve Strogatz, a professor of applied mathematics at Cornell University.
I'm Dr. Eugenia Chang. I'm scientist in residence at the School of the Art Institute of Chicago.
My name is Shankar Venkataramani. I'm a professor in the math department at the University of Arizona.
I'm Dan Finkel. I'm a mathematician and educator and the founder of Math for Love.
Okay, that's more mathematicians than I can count. Well, actually, it's not. It's only 4. But don't let this quorum get your topology in a twist. These mathematicians come in peace. Their common denominator is that of wanting to correct whatever gives you algebraic anxiety.
Which may have started in school.
We give students a mathematical miseducation when we give them an experience of mathematics that is just dead facts and appeals to the teacher's authority. And if a teacher loves the subject, they want to share that love with the students. If they themselves have been coming from a negative experience, if they never were exposed to what was beautiful in mathematics, what was so compelling about mathematics, it's very hard for them to even know what the positive vision is for their students.
Dr. Cheng is ready to help more people get a taste of math. In fact, her approach is one you can really sink your teeth into. She cooked up a plan to make digits more digestible and trigonometry more tasty.
And it was as easy as, yes, we're going there, how to bake pi. That's pi, as in the ratio of a circumference to the diameter, 3.141592. You get the idea.
When I say that math and cooking have some things in common, people often go, oh, because it's about ratios, right? And if you want to scale a recipe up, then you have to multiply everything by 2. And that is true, but that's not the deepest way in which math and cooking are related. And I think it's about taking some basic ingredients and seeing what you can make from it.
I'm going to see what I can make today in my kitchen. Let's see, what am I going to need for this? Measuring cups, measuring spoons. Okay, that, whatever that is, I could use that.
Eugenia, almost every chapter of your book, How to Bake Pie, begins with a recipe for a dessert. And if I didn't know better, I'd think you're bribing us into liking mathematics, or maybe trying to flog a diet plan.
Well, I love math, and I also love food. And in the course of my teaching undergraduates and various levels of high school and middle school, I've realized that many people love food more than they love math. And it's true that when I was teaching at the University of Sheffield in the UK, I realized that food did wake my students up. And not to say that they were asleep, but they perked up at the mention of food. And I didn't just want to bribe them in that kind of slightly cheesy way where you bring chocolates in and you say, anyone who answers a question gets a chocolate. So I thought that was a bit superficial. But I realized that I could actually tell stories about food that depict and illuminate mathematical principles. And that's what I started doing, and that turned into that book.
Okay, so into this bowl goes flour and the baking soda, and I'll whisk that together. And for this recipe, I'm actually going to melt this butter.
One of the reasons that most of my recipes are for dessert is, first of all, I really like dessert. And secondly, one of the reasons I like cooking dessert is that you take some things that look really basic and you do something almost like magic to them, and they become something that looks really different. You know, you take butter and sugar and flour and eggs and you make cake. And cake doesn't look anything like butter, flour, sugar, or eggs, which I think is really exciting, and it's like what happens in math. Whereas I love steak, but if you take a steak and you cook it, it kind of goes from looking like a steak to looking like a steak, just more cooked, which is a little bit less transformative to me. And the thing I think is so wonderful about math is that it is transformative. You take some basic starting things like numbers and shapes, and you build amazing things.
Egg. And now, of course, the most fun part, chocolate chips.
So let's say I started with the ingredients, addition, subtraction, multiplication, division, and just one number, which is the number 1. And I could ask, what could I make from that? Just from those 5 ingredients, what's possible? Well, I could take 1 and add it to itself, and then I get 1 plus 1, and that's 2. And I could take 2 and multiply it times itself, and that gives me 4. And I could take the 1 again and divide by 4, and now I have 1/4. And I could keep building with those materials, and every time I use them, every time they mix together, they produce something new. And suddenly I have a whole number system, which I've built out of just a few simple ingredients.
And then I mix this until it's really smooth. And the only thing left to do is bake.
Well, in your book, you alter the recipe for a cake so that it is gluten-free, sugar and dairy-free. What's that an analog for?
It was a bit of an extreme case where I had so many friends, and many people have this experience, had so many friends coming to a party who had some sort of dietary requirement that I tried to make a dessert that would suit all of them. And math often happens like that. You start with something that is well understood, and then you alter it a bit, and then you alter it another bit, and then you alter it another bit, and you see what things you produce like that. And that is how we make new math. Sometimes people say to me, how can you do research in math? You can't just invent a new number. And that's true, but we don't just invent new numbers. We invent whole new worlds and types of things by taking the things that we already understood and just slightly altering them, or saying, oh, I want this to do something slightly different. And that is how we came up with the new world of the imaginary and the complex numbers.
Historically, imaginary numbers come from this problem, which is certain equations asked you to take the square root of a negative number, and it just doesn't make sense. Because when you multiply 2 times 2, you get 4. Negative 2 times negative 2 is also 4. So there didn't seem to be any way to find a square root of negative 4. There was no way to find something that multiplied times itself to make negative 4. But if we just say, let's just invent it, let's just assume that it exists, it's imaginary, but let's allow it to exist, we invoke and somehow just believe into existence a new mathematical object, which we can start to play with. And later, it turns out that we actually have a pretty good model for how to imagine what that imaginary number is, which just has to do with rotations. So if multiplying times a negative number spins you around 180 degrees, multiplying times an imaginary number just spins you 90 degrees. And it ends up actually being far more intuitive than anyone would have thought.
For this dish, I'm going to be creative and do a substitution, a kind of radical substitution, and see what my husband thinks of that.
What is this?
This is pesto with kelp noodles. It's not pasta, it's kelp noodles. Okay, try it.
All right. It's kind of hanging on my fork like spaghetti would, maybe a little stiffer.
It's kind of...
It's really, really different than spaghetti. It's crispy. If worms had exoskeletons, it would be kind of like that.
Or you say something like, oh, well, an ordinary world doesn't have infinity in it, and I want a world that has infinity in it, so I'm just going to make a new world that has infinity in it. And making those inventions is something that many people enjoy doing in the kitchen. You start with a recipe from a book, but then you don't want to just follow somebody else's recipe, so you alter it to your own tastes. And actually, we do that a lot in math. It's just unfortunate that in math class, you usually just have to keep following somebody else's mathematical recipe.
Is there any concept in math that is the equivalent of improvising in the kitchen? The thing you do, and I don't know, the cupboards are bare, the refrigerator is empty, but you find a few items and with some ingenuity make something delicious out of it all.
Yes, there's a chapter in which I talk about internal and external motivation. And internal or intrinsic motivation is where you do that. You look around your cupboards and you go, well, here's what I've got. What can I make? As opposed to making a list, deciding on a recipe you're going to make in advance and going around the grocery store, picking up all those ingredients. And the kind of math that's like going around a grocery store deliberately finding ingredients is like having a particular problem you're definitely trying to solve and then going around finding all the pieces of math you need to solve it. And that is, in a way, a more obvious way of doing math. But there's another way where you look at what you have and explore the situation that you've already got and see what new things you can make without having a particular goal in mind.
Okay, let's see what we have in here. Old broccoli, red bell peppers. I can use this old stock. Oh, anchovies. They might bring flavor. And in the freezer, we have these old chicken bones and some very frozen asparagus. Put all that together and then cook it. We'll either have broth or soup, or you know what? I don't know what we're going to have, but it's a way to use all of these old vegetables.
So if we're just playing around, we don't know what we might invent. And often the animating question for mathematics and mathematics research is what's possible in this universe, in this system. An example might be knot theory. Not very many people know that the study of knots is a hot topic in mathematics. And if we just say you take a loop and it's going to be knotted in different ways, how many different possible tangles can we get and how can we tell them apart? Just understanding what the possibilities are require us to think in new ways, and we really don't have any idea what we're going to find from that very basic starting point.
And actually a lot of math goes like that. It doesn't have a particular goal. It's not trying to solve a particular problem. And we invent new things. We invent new shapes. We invent new worlds.
I think about mathematics as doing research 200 years in the future. And you're constantly dreaming up stuff that feels like it could never have a function or never have a use. And a lot of times it doesn't. The things that I studied had to do with very idiosyncratic objects that were four-dimensional, and they were called K3 surfaces. I don't think anyone has a use for the work that I was working on. But often the things that we think are the most useless, like how do we multiply enormous numbers together so big they'll break a calculator? How do we actually manage that? And figuring out how to multiply and divide them and unmultiply them, factor them, ended up being hugely important to cryptography, even after they were put forward as an example of something that could never have any use because the numbers were bigger than the universe, bigger than anything in the universe, impossible to use, and yet useful within 50 years of someone claiming they could never have a use.
The wonderful thing about it is that although we don't have a particular goal in mind when we're doing that kind of math, it often turns out to be amazingly useful later, sometimes much later. For example, the Platonic solids are the very, very symmetrical three-dimensional shapes that mathematicians were thinking about 2,000 years ago. And it really took 2,000 years before any application was found for the use of the icosahedron, which is the most complicated one that involves 20 triangles. And in the 1950s or so, it was discovered that viruses mostly are icosahedron shaped if you look at them under a microscope. And that was just a shape that mathematicians dreamt up by a bit like looking around your kitchen and going, what can I make? So they looked at triangles and thought, oh, what shapes can we make with triangles? And there was no particular use for it for thousands of years, and then there was.
It sounds like nature found the applications for the Platonic solids, as you call them, sooner than the humans did.
Yes, nature is very powerful like that, and that's why there's a lot of math in nature. Well, at least I think that's why there's a lot of math in nature, because nature might well be better at it than we are.
So finally, Eugenia, when people write you about your book here, are they commenting on the math or are they commenting on your recipes?
Mostly they're commenting on the math, but I do love it when my students come to class and say, I made this recipe. I made the recipe at the beginning of the book. And I also love it when they say they changed it a bit, because then they're really taking on board the idea that you can make your own things up. And I wish that we could do math education in such a way that everyone feels like they can experiment a little bit by themselves rather than just have to follow what someone else told them to do.
Eugenia Chang, thanks so very much for speaking with us.
Thank you for having me on.
Eugenia Chang is a scientist in residence at the School of the Art Institute of Chicago, and she's the author of How to Bake Pie. And she finished there with a wish that mathematics classes were taught with more play. On that note,
I've been working on the problem of how to transform how math is taught and learned. I know that it's possible to teach math so kids at least have a chance to fall in love with it. And I have a lot of ideas about how to make that happen.
That's coming up later in the show. But first, and more important, Molly, did you have any of those test cookies left over?
Yes, how many would you like?
Well, that's a different question from how many should I have, but I'll start with one. Oh, you have them all wrapped up. My God, these are the size of pizzas. I'm just going to break off a piece here.
How are they?
They're actually really good. They're good.
Actually.
Well, they have a nice geometric shape. They're a flattened cylinder, which is to say cookie-shaped.
Dr. Cheng said that because there's a lot of mathematics in nature, we might find inspiration there. Next, a new generation of squishy robots inspired both by the animal world and the curve of a potato chip.
Where will we take you next? We're following math's paths on Big Picture Science. So the good news is your business is growing and you need to hire some folks to keep the momentum up. The bad news is, just how do you do that effectively and quickly? The answer, Indeed. Indeed.com is the #1 job site in the world because Indeed gets you the best people fast. Unlike other sites, Indeed gives you full control and payment flexibility over your hiring. You only pay for what you need. You can pause your account at any time, and there are no long-term contracts. Plus, Indeed provides powerful tools to make your search that much easier, like sponsored jobs, which are shown to be 3.5 times more likely to result in a hire. With 73% of online job seekers visiting Indeed each month, Indeed is going to get you the important hire you need, just like they have for over 3 million businesses. Right now, Indeed is offering BiPi-Sci listeners a free $75 credit to boost your job post, which means more quality candidates will see it fast. Try Indeed out with a free $75 credit at Indeed.com/bigpicture. This is their best offer available anywhere. Go right now to Indeed.com/bigpicture. Terms and conditions apply. Offer valid through September 30. Equations, integers, polynomials, non-Euclidean geometry. We're speaking the language of mathematics in this episode of Big Picture Science. And what's more appealing than the geometry of this potato chip? I mean, look at it. This chip it's really a disc with a double curvature. If I place it here on the table, the sides remain raised like wings. That shape there, that's what's called a hyperbolic sheet, a shape that's particularly well adapted for stacking. This point of contact on the table where the potato chip rests is called the saddle. But I have to say it's hard to think of the geometry with all that salt and starch.
So a hyperbolic sheet or a saddle surface is surfaces which, as you go out from a center, they grow faster than you would expect a flat object to grow.
The gracefully curving and often colorful sea slug may seem like humble beginnings for the next generation of robots, but University of Arizona mathematician Shankar Venkataramani says it's not so much that his engineers picked the sea slug for inspiration, but it kind of picked them when they began looking for hyperbolic sheets in nature.
And then we found that these shapes that we get, you see them in leaves, in flowers, and leaves and flowers, these are static in a sense. So more recently, we started looking at how do these things move. And that's when we came upon sea slugs.
Earlier we heard about what happens when you play with mathematics and you break the rules. Well, hyperbolic sheets are another example of that.
For the longest time, people believed there was just one geometry, and so hyperbolic surfaces, they have sort of philosophical significance in math because it was the first time that people realized that just because somebody set down some axioms 2,000 years ago, it doesn't have to be true. So in particular, in a hyperbolic sheet, you don't have the property that two lines don't intersect only if they're parallel. In fact, you can have infinitely many lines which are not parallel, which don't intersect. So some of the very basic things that we take for granted in Euclidean or flat geometry are not true in hyperbolic geometry, and that's part of the reason why mathematicians care about this a lot.
Another is that the hyperbolic sheet is inspiring a new generation of swimming, crawling robots.
Shankar, please describe why the world needs soft, squishy robots.
Because they're cool, because they can do things that hard robots couldn't. So the larger ones, they're useful, for instance, because they could both swim and walk. Large is easier, but there's nothing that stops you from making them small.
These are robots that could go in many different mediums. They can move through air, obviously, but also through water and other substances, and it's because they're malleable?
Yes, it's because they're malleable. They have a great degree of flexibility, and we can exploit this in different ways. They are soft and they have a very small energy budget. So you don't need to store a lot of energy and you don't need to use a lot of energy to manipulate these shapes. Things like in space exploration, for instance. And the other feature, which I also think is important, is just like sea slugs, they don't have joints. And while not having joints makes it hard to move, it also makes it that there's much less wear and tear.
So the sea slug has a particular way of moving, and I wonder if you could just describe what it looks like when it moves.
Yeah, so sea slugs and also marine flatworms, they're unique in that they don't have a hard skeleton. They don't have joints. They can't move like fish move fins relative to the body. They can't do that. So the way they need to get around is somehow change their entire shape in a way that you cannot stretch or increase their length or decrease their lengths by a large amount. So with small two-dimensional changes, they want to make big three-dimensional shape changes.
Your description of their movement sounds like something that would interest a biologist. You are a mathematician, so what are the mathematical conundrums that the movements of the sea slug present to you?
It's what we might call rigidity. So if you take a sphere, for example, you cannot change its shape without doing something very violent to it. You take a ping pong ball, if you want to change its shape, you essentially have to crush it. But a sea slug is very different in that its mathematical structure is such that it has enormous flexibility. So all we say is we have this object, we are not going to allow it to stretch at all. What can it do?
Okay, so it has to be nimble in some ways, malleable, but also has to have structural integrity.
That's exactly right. That's a very nice way of putting it.
What do you think the ancient Greeks from 2,000 years ago would think of you applying their geometry to the creation of a sea slug robot?
I would like to think that they'd be pleased with how logic and sort of the way of doing math and science has survived all these centuries and is still giving hopefully useful things.
Well, Shankar, how far have you gotten on creating this soft robot that moves like a sea slug?
So we have it on a computer, but there's a big question. One is we know what are the shape changes we need to get it to move, but these shape changes, unlike, say, folding paper where you have hands which apply external forces, they all have to come from inside the body. And this is not something that we fully understand yet. And then we need to figure out a physical mechanism that can mimic how to make these internal forces to get these robots to move.
Well, finally, Shankar, the sorts of robots that are being designed now and the places that you are finding your inspiration from, biological organisms to the talks that your colleagues are giving about the kinds of robots they're designing, suggests that we're really in the era of a fundamentally different kind of robot from the robots that we have in our mind's eye, the stiff, large, clunky titanium sorts of robots. Why is our imagination not limited anymore to those awkward robots?
This, I think, is true in many areas. So engineering is, at least in the past, was based on keeping things extremely stable. You know, you build houses or bridges that are really strong, that can take 10 times the load that it was supposed to take. But now in how they do, say, satellite motion planning or in other things, these ideas from chaos and nonlinear dynamics, what you want is flexibility. So I think the future is in this kind of work where there's flexible, easily changed, sort of on the brink of instability kinds of systems. Because when you're on the brink of an instability, a small input can lead you to many different places.
Shankar, thank you so much for talking to us about these soft robots.
Thank you very much.
Shankar Venkataramani is a professor of math at the University of Arizona. His sea slug robot is based on a nifty bit of geometry, which is, of course, one of the oldest branches of mathematics. In high school, it's a prerequisite for another, somewhat younger branch of mathematics, equally inspiring, calculus.
Infinite Powers, How Calculus Reveals the Secrets of the Universe, is a book from one of the world's leading mathematicians, a professor of applied mathematics at Cornell University, Steve Strogatz. And his sweep of history reveals the beauty of what he says is one of humanity's greatest achievements.
Steve, while the Greeks were able to write the definitive treatise on plane geometry, 2,500 years ago, calculus doesn't come around for another 2,000 years. Why? What was obscure about this amazing bit of math?
Most historians would say that calculus is a creation of the 1600s, more or less simultaneously in two places, by Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany. And you could ask, if the Greeks had geometry, and certainly the Egyptians and Babylonians were doing very good geometry, like 500 BC, what took so long? And I think the answer is mainly algebra, that the calculus that we teach today, as all students will know who've taken it, is rife with algebraic manipulations. But historically, calculus had to wait for geometry to merge with this, what was at the time, newfangled subject of algebra that was more or less perfected in the Middle East in places like Baghdad and Cairo. And then when it migrated to Europe in the Middle Ages, then when it collided with geometry, first there had to be a new subject of analytic geometry, the fusion of algebra with geometry, where you represent shapes with formulas and equations. And then that raised all kinds of questions that pretty soon led to calculus.
Does it make a difference whether we say that calculus was invented or discovered, or is that kind of a philosophical point?
It's a philosophical point, but it's a really interesting philosophical point, and I'm not sure how I would answer it. We certainly invented it, we, the human race, in the sense that people created it, like Mozart created his pieces of music or Shakespeare his plays, but it has an extra quality to it, all of mathematics does, that it feels like it's there independent of human beings. It's a little bit of a mystical statement, but it when you discover facts about pi or about the quadratic formula or whatever, it feels like those things were out there waiting for us. We didn't invent them. They're just true. And I don't know, this is philosophical. I can tell you, as a working mathematician, almost all working mathematicians would say that we are discovering the mathematics that we find.
That it's part of the universe. And you're just picking up, brilliant little pebbles off the beach kind of thing?
Yes. Funny you would mention that word, actually, pebbles, because that's where the word calculus comes from. Sometimes if you'll go to the dentist and they're scraping that gunk off your teeth when you go in for a cleaning, the dental hygienist will refer to it as calculus. She'll say, I'm scraping the calculus off your teeth, because calculus comes from the same root as words like calcium and chalk, and it means little pebbles, which used to be used for counting.
If someone were to ask me, well, who came up with calculus, I would have said, of course, Isaac Newton. I say, of course, because I think that would be the answer you'd get from 8 out of 10 people who had an answer at all. And yet, in the Renaissance, you had Galileo, you had Kepler, Descartes, Fermat. I mean, these were brilliant folk, but they didn't do what Isaac Newton did and, kind of formalize calculus. Was he just brighter than they were, or was he just was he just lucky? Or
Well, he was phenomenally bright, that's for sure. I don't know that I would say he was brighter. Maybe he was, but I don't think that was his extra advantage. He, as he famously said, stood on the shoulders of giants, and he had people like Galileo and Kepler and Descartes in mind when he said that. That if I have seen further, it's because I've stood on the shoulders of giants. He used ideas that they had developed, but he synthesized them and systematized them in a way that went beyond anything before him, so that what had been a sort of hodgepodge of different mathematical techniques, he was able to combine into a machine that was so systematic and so streamlined and actually easy to use once you learned how to do it, that you could teach it to ordinary high school students.
The popular story here is that Newton developed gravity and the need for calculus because he witnessed a falling apple. I kind of wonder about that, but he was really trying to explain the motions of the planets and the comets and so forth. It was astronomy that motivated his mathematical invention, not fruit. Isn't that so?
Well, yeah, interesting point there. He did absolutely find astronomy fascinating, the motions of comets, the planets, also celestial phenomena about the tides, the shape of the Earth. So when he eventually published his masterpiece, Principia Mathematica, the mathematical principles of natural philosophy, he did seek to unify what we knew about the laws of motion. I mean, he put forward the laws of motion on Earth and in the heavens and showed that this same system of laws could explain both. So this was a really big scientific advance because, if you think back to like the time of Aristotle, and who had a great influence for thousands of years, people thought of the celestial realm as somehow different and perfect and unchanging, whereas the Earth was plagued with decay and rot, and things would live and die, and so it was a very transitory kind of place, whereas the heavens were permanent. But Newton showed that was all just a lot of mumbo jumbo, really. Scientifically, the same laws explained phenomena he could see in both. Can I just jump in with the apple story, actually? Because
was that true?
Well, we don't know for sure if the apple was true. We do know that there's an orchard at Newton's childhood home, and he may have developed this apple story to kind of just get rid of people who were asking him questions about how did you come up with the law of gravity. It could have been that. It could have just been a device to make people stop bugging him. But there is some indication that he thought about objects falling, and it could have possibly been an apple. Not likely that it fell on his head, but I think it's plausible that he was thinking about objects dropping to the ground, like apples falling from a tree, because in one of his notebooks, he talks about thinking about the moon, and why is the moon always there? Why doesn't the moon just fly away? And he asked himself the question whether whatever it was that was holding the moon in its orb, as he put it, might be the same thing that's holding us to the Earth and that causes he didn't say an apple, but that would cause things to fall to the ground. And using his famous inverse square law, he figured out that this could explain the orbital period of the moon, that it seemed like this one law, his law of gravity, could explain both the moon and the falling of objects near the surface of the Earth.
We take it for granted now that with Newton's treatise there, with his mathematics, we can explain the motions of the planets. But, that's really an amazing and astounding thing, is it not? I think even Einstein was astounded by the fact that mathematics can describe the universe.
It is astounding. It's maybe the most profound mystery there is. This is something that Einstein always was agog at. He has all these great quotes, one that's maybe a little bit of a misquote, where he says the most incomprehensible thing about the universe is that it's comprehensible. But it comes close to expressing sentiments that Einstein actually had, that, why should this world, this universe that we live in, match up so neatly with the math that human minds have invented or discovered. Which, if that question doesn't sound strange, or if you don't see what the mystery is, keep in mind that we're just a few steps removed from the apes, from the primates. And yet, with our puny logic, we can somehow predict what these planets so far away from us that we can only see as little specks. We can understand their strange motion, even though we've never even been to them. And not just that, but we can look inside the atom. We can figure out all sorts of things about, ups and downs of wildlife populations or the changing weather. That somehow this one language of math, and specifically calculus, is just the best tool we've ever devised or discovered, however you want to think of it, for predicting the workings of the world around us.
Well, finally, Steve, in writing your book, what was to you the most, surprising phenomenon that calculus unraveled?
Well, there are many. One that sticks in my mind because it was news to me is the development of CT scanners, which, when people used to go in for x-rays, for hard structures like bones and teeth, x-rays work very well. But for soft tissues, like, say, if you wanted to look for a brain tumor or a blood clot in the brain or a hemorrhage, it was known that x-rays wouldn't do you any good at all because under x-rays, the brain would just look like an amorphous, gray, cloudy mass. You wouldn't see anything. But in the 60s, two different scientists in different parts of the world, one in South Africa, one in England, came up with the idea that if you didn't just shoot x-rays in one direction, but if you shot them in many different directions through a sample, you could use calculus to recombine the information, and maybe you could actually see what was going on in soft tissues like the brain. And that soon led to the development of the CAT scanner or CT scanner that revolutionized medicine. You don't normally hear that calculus was such a pivotal ingredient in that.
Steve Strogatz, thanks so very much for speaking with us.
Thank you, Seth. It's been great to be with you.
Steve Strogatz is a professor of applied mathematics at Cornell University, and he is the author of Infinite Powers, How Calculus Reveals the Secrets of the Universe. It's interesting, I don't know if you've noticed, Seth, but we've had at least one food item mentioned in each one of these discussions about mathematics.
Well, could that be because people are hungry for knowledge? Do you think that's it?
Maybe that's it. I like that. We had all the baking, the chocolate chip cookies, potato chips, and the food in this discussion was Steve Strogatz?
No food. Newton never ate that apple. That's just not true. We've heard many ways that mathematics can inspire, but some say a sure way for that appreciation to actually hang around, make math appealing in school.
We need to give genuine, authentic questions that are accessible to the students, that are at the right level for them, and give them the space to explore them and make them their own.
How to make learning math a joy for students next.
As we continue down math's paths on Big Picture Science. There are countless reasons to find mathematics inspiring, sure, but also relevant and beautiful, as we've heard, even an infinite number of reasons. So now the question we get to is, how do we counter the chorus of young people bemoaning their boring math classes? Well, mathematician Daniel Finkel says his Seattle-based organization, Math for Love, offers a successful approach to deploy 1 part enthusiasm plus 1 part play plus 1 part question-based teaching.
Dan, according to you, we have very low expectations for math class. And now, is that because for many students, math is a grind, or do we just expect it to be? In other words, does math simply suffer from bad PR?
There definitely is a PR problem, but for me, it often begins with what our expectations are, and that is both from the administration and systems, but also from the teachers. And if a teacher loves the subject, they want to share that love with the students. If they themselves have been coming from a negative experience, if they never were exposed to what was beautiful in mathematics, what was so compelling about mathematics, it's very hard for them to even know what the positive vision is for their students.
I think you point out that a lot of mathematics, the way it's taught now, is you memorize formulas, you memorize how to do things. It's by rote. Is that the problem?
The problem with math class is that we give answers before we actually articulate questions. So this leads to a situation where we just have to memorize a ton of stuff with no context. And I'll give you an example. So one thing that everybody has to learn at some point is what's known as the commutative property of multiplication, which says that you can always switch the order when you multiply. 5 times 7 equals 7 times 5. You know, like, let's say I had 5 nests with 7 eggs in each nest. That's going to be the same number of eggs as 7 nests with 5 eggs in each nest. Doesn't matter the order. And that's just something that students are supposed to memorize. But it's actually astonishing. If you stop and think about that, why is it true that 45 bags of 36 candies is the same as 36 bags of 45 candies? It doesn't seem like it should be true. Most of the time, you can't switch the orders of things. Like if I tell you you're going to put on a parachute and then jump out of an airplane, that's very different than jumping out of an airplane and then putting on a parachute. Most of the time, you can't switch things. In this case, you can. It's not obvious why. And it's something that we just tell kids and say, memorize this. This is just something that's true. What we never ask students to do is say, is that true? Why would it be true?
So is this why some students will say that math is boring? It just feels like you're memorizing these rules. You don't really understand them. And also why some people will report they just fear math.
Yeah. My experience is that all kids love math when they are 2, 3, 4, 5, 6, 7, 8 years old. It is just in their blood. There's something about finding patterns and structures and numbers and shapes that is so compelling. But when we teach it improperly, what we do is say, whatever your common sense is, ignore that. I want you to forget your sense of understanding, your natural ownership of this subject. Let go of that and just take my way. And it becomes something people feel alienated from.
Now, before we continue this conversation, we are talking about mathematics. We're not talking about arithmetic per se. And can you just remind us of the difference?
Yeah, arithmetic is a very, very, very small part of mathematics. And I think of mathematics as the art and science of patterns and structures and numbers and shapes. And arithmetic is really a set of tools for dealing with numbers in some specific ways. It's useful, it's a great thing to learn, and it can help you tackle more sophisticated ideas if those tools are under your belt. But it really is just a small tool set and a tiny part of mathematics.
And we're going to come to the solutions in a moment, but I wonder if you could just put on your mathematician's hat now really tight and describe a mathematical formula or a mathematical process, and you can go full on math on us if you want to, that just delights you. Can you give us one?
Oh boy, yeah. Okay, if you want full on math. So here was a question that I remember I was in 9th grade, and this is actually a question on a test, but it was design a game using a single fair coin that you have a 1 in 3 chance of winning. And this is such a wonderful question because there's actually a very simple, almost obvious answer to it, and I did not see it. And I worked on this question for hours.
Okay, let me repeat that. And also, it surprises me that you started with design a game. I thought you were going to just start reciting formulas. But okay, so it's design a game where you have a 1 in 3 chance of winning. Is that it?
That's exactly right. Design a game where you have a 1 in 3 chance of winning, and you're only using a fair coin. And there's cheating ways of doing it where you can draw 3 sections of a circle and toss the coin into it. But that's not the spirit of it. It's really, you flip the coin, it's either heads or tails, it's 50-50 each time. And can you come up with a game that you have a 1 in 3 chance of winning? I love this because it gives a sense of how broad and creative mathematics can be. You can come up with any game you want as long as it fits within the structure of that problem. And as I was playing around with it, what I found is that, like, if you say flip the coin 5 times and if this happens, you win, that doesn't work. And if you say flip the coin 100 times, and if this happens, you win. It doesn't work. There's something baked into the mathematics that prevents that approach from ever working.
What is the solution? And you might need to just break it down for us. What is the
Sure.
solution to this conundrum?
So here is the classic solution to this problem. We want to design a game we have a 1 in 3 chance of winning. So I'm going to flip the coin twice. I can either get heads, 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 tails, tails, heads, or tails, tails. That's 4 options. I'll declare one of them a do-over. Let's say tails, tails. So now there's only 3 remaining options that are not the do-over. Heads, 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 tails, or tails, heads. Of those 3 options, I'll choose one of them to be my winning situation. Let's say heads, heads. And now I have a game I have a 1 in 3 chance of winning. I flip the coin twice. If it's heads, heads, I win. Heads, tails, I lose. Tails, heads, I lose. Tails, tails is a do-over, and I play again. Because there's a do-over inserted, that game could last any length of time. But what was so interesting to me is that I didn't think of that. And because I didn't get the easy answer to the problem, I ended up thinking about it for years and years later.
Years? Literally years?
Literally years. And this is almost every math problem that I fall in love with, the math problems that have changed my life, stay with me for years.
I think what we should offer to do, Dan, is we'll post that solution on our website if a couple people want to read through the answer to the coin toss question. But I think the key here is that we want to take the enthusiasm that you just shared and bring it into the classroom. And how do we do that? What are you proposing is taught differently?
What is required to teach math differently is to invite students to the genuine mathematical project, what mathematicians do. And what this means is we need to give genuine, authentic questions that are accessible to the students, that are at the right level for them, and give them the space to explore them and make them their own. What it has to feel like is they're not doing somebody else's process, but they're actually owning their own thoughts, owning their own material.
Can you give an example of a question? Is it like the coin toss question, or is it sort of like 3 people are in a boat, 2 of them are wearing white hats, and one's wearing a black hat? Or what kind of question?
Right. So fundamentally, any question that grabs students' attention is worthwhile. Let me share one that I often do with students. And this is another game called NIM. And I'm going to play it with you right now. All right? The goal of the game is to be the first one to say 0. We're going to start at 10, and you can take away 1 or 2 from that number, and then I'll get to take away 1 or 2, and we keep going back and forth until someone says 0. Okay, so it starts at 10, I'll take away 1 and say 9, and now I pass the 9 to you.
Okay, I'll take away 2 and say 7.
Great, I'll take away 1, 6.
I feel like I'm going to get caught in something. I'll take away 1. I'll take away 1, 5.
I'll take away 2, 3.
And the goal is to get to 0?
Yep.
I'll take away 1, and then I get 2.
And now I can take away 2, and I say 0. I win the game. Good game, first of all. But it turns out, because I understand this game so well, I consider myself a NIM master, actually. I got to be a NIM master by losing many, many games. But now I understand that game so thoroughly that I'm confident we could start at any number, and I would always be able to be the one to say 0. Now, just sharing that with students, just bringing a student up to the front of the classroom and beating them at this game plants a question right away, which is, how do you control these things? How do you own this game so completely that you can take the next steps and start to figure it out on your own? As soon as the kids want to learn, none of this takes that long. Just the hard part is that teaching things to students who don't want to learn is very time-consuming.
I know that you've designed some games, and you've also been working with schools, encouraging them to adopt some of these methods. Have any of the schools done that? What have the results been?
Yeah, so Seattle Public Schools adopted our play-based curriculum for their elementary summer program called Summer Staircase. And what we found is that students coming in who are often in danger of falling off course in mathematics, if they took the program for 2 or more years, they were over twice as likely to pass the state test for proficiency in mathematics. So I think there is some real evidence that a play-based approach is actually one of the most powerful approaches for students.
Daniel Finkel, thank you so much for speaking with us.
Absolutely my pleasure.
And the coin toss solution will be on our website, bigpicturescience.org.
Daniel Finkel is a mathematician and founder and director of operations at Math for Love. As we wind down our program here on mathematics, I'd like to say something a little bit personal about mathematics, often referred to as the queen of the sciences, and yet in many ways it's not even a science, but it is the ultimate in creativity, in skill, and frankly, in beauty. Mathematics has no rough edges, and from my point of view, it's perhaps the purest thing in the universe.
We'd like to enumerate those who help make our show. Senior producer Gary Niederhoff, assistant producer Sarah Derwin, and operations manager Barbara Vance. I'm executive producer Molly Bentley.
Thanks also to financial support from Rena Shulsky-David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit education and research organization whose scientists study the origin and nature of life, including the formation of solar systems. I'm the Institute's senior astronomer, Seth Shostak, and I'm mostly three-dimensional.
Your ears have been attuned to an episode of Big Picture Science called Math's Paths. And if you'd like to hear more Big Picture Science, well, you'll find past episodes in our archive at bigpicturescience.org, and our website has links to the guests you heard, as well as the solution to Daniel Finkel's coin toss puzzle.
You may be listening to our radio show on the air, but did you know we're also a podcast? And you can make sure you never miss an episode by subscribing to the BiPi-Sci podcast on iTunes, Google Play, Stitcher, Spotify, iHeartRadio, Pandora, or Himalaya.
Gentlemen, this computer has an auditory sensor. It can, in effect, hear sounds. By installing a booster, we can increase that capability on the order of 1 to the 4th power.